All right. Having talked about the physical phenomenon that give rise to noise in semiconductor devices, now let's talk about the actual model that we can have for noise in semiconductor devices, particularly diodes and transistors. So let's start with a diode, with the p-n-junction diode, right? If you think about a p-n-junction diode, something like this, you have a p-type material and n-type material, so that's a p-n junction, and then you have a depletion region, and then you have current flowing in it. Let's say it's forward biased, and we know that the energy band diagram looks like this. You're lowering the energy in the forward bias. You're lowering the energy barrier, so more electrons, exponentially more electrons and holes can pass, and that's why you have the exponential behavior. Now, as you can imagine, and as you can see, the process of an electron passing the barrier is a distinct process, and therefore it should give rise to shot noise. So what else is there? If you think about the semiconductor, these pieces of semiconductor are not perfect conductors, right? They have a resistance, a physical resistance here, right? And as such, these physical resistances will have what kind of noise? And they will have to have thermal noise, right? Johnson noise, because they're just like any other, and we had a thermodynamics argument about whether there should be Johnson noise or thermal noise when you have a resistor. Fluctuation, dissipation, loss corresponds to noise whenever you have physical loss. So if you think about a diode, if we didn't have these things, how do we model the diode from a circuit perspective, from a small signal perspective? Now, a small signal is a pretty good thing as far as noise is concerned, because noise is generally very small. So most of our noise calculations would be small signal analysis, which is reasonably well justified. So, but from a small signal perspective, an ideal diode, or like a semiconductor diode whose current looks like an exponential, right? I is some is e to the power of Vd over Vt, where Vt is Kt over Q, will have certain kind of, it's more accurately this minus 1, but it will have a certain kind of small signal resistance, right? We've talked about this before. What is the small signal resistance associated with that? You have an IV characteristic. You have ID versus Vd. That's an exponential, right? And this exponential, at any point, you can actually look at the slope of that exponential, and it is an Rm, right, that we've seen. So if you look at the slope, which is basically like 1 over Rm, the slope would be ID over Vt, or QID over Kt. So you have a model for the diode involves an Rm, right? It also has some sort of an R series. This is the physical resistance, right, contributed by these guys. This is the physical resistance, ohmic resistance in series. Now, if you think about it, the series resistance will have a noise source, right, associated with it. So we can think about it as a noise source, a voltage noise source, whose value would be what? Whose power spectral density, voltage power spectrum would be what? So this is V thermal. Would be, we've calculated this before, right? 4 kT RS. Right? It's 4 kTr as a voltage. Now, how about this shot noise? Where would that appear? Well, it would appear across the junction, this exponential behavior, right? So that you can think about as a current source in parallel, I shot F, which is basically 2QID. So let me just clean it up a little bit. I shot squared over delta F equals 2QID. ID being the DC current passing through the diode. And then on top of that, you can potentially have some sort of a flicker noise source. Which we can show, or 1 IF over delta F, IF squared over delta F, of some K, something related to ID, generally with some power, divided by F. So this is the noise model, the complete noise model for a diode. So these are the prominent noise sources in a p-n-junction diode. You have thermal noise associated with the physical resistances. You have shot noise associated with the distinct event of transition of charge carriers, the electrons and holes, across the barrier. And then you have flicker noise because in general you may have imperfection in the crystal and other things that will produce a flicker 1 over F noise spectrum. So we've gone from this model of RM and RS to something more sophisticated that looks like that. So that's for the p-n junction diode. Now, okay, so that's for the p-n junction diodes. How about the bipolar transistor, a BJT? So let's look at it next to this thing. The BJT, if you remember, looks like this. You have 3 junctions. Let's say it's an NPN, and this is the emitter. So you have this one being forward biased and this junction being reverse biased. And what happens in the energy band diagrams is that you have lowered this energy band for the N, so more electrons from the emitter can go into your base, and most of them in a properly designed transistor will end up in the collector. And some of them, a small fraction of them, are recombining or back injected into the emitter in the case of, and that accounts for the base current. We've covered these things before. We've talked about these when we talked about the device physics at the beginning of the class. So what happens as far as noise is concerned? Well, let's look at the small signal model first. Let's draw the small signal model. So you have an R pi, and you have a GM V pi. And we can include the RO or not include it. Let's not include it in this case. And then you have something like this, right? Again, the question is that would R pi generate thermal noise? The same question would have been applicable here. Does Rm in the diode produce thermal noise? Well, remember, thermal noise is only generated from resistors that actually represent a real physical loss, right? Fluctuation dissipation theorem. So these are not real losses. R pi, for example, or Rm. These are derivatives. These are just basically measures of slopes, right? These are fictitious resistors, if you will. On the other hand, you may have some real resistances. For example, where? For example, you're in series with your base. You do have, your base is a thin thing, and then you have a series resistance. And that series resistance does exhibit. So let's say there's an RB, right? And that RB would exhibit what? Thermal noise, right? So for example, that one would produce what kind of thermal noise? It would produce a voltage thermal noise, VB squared over delta F, of 4 kT RB, a voltage source in series. Or you can actually model it as a current source in parallel too. They're always convertible to each other. But that's what you get. Now, so that's one clear one. Now, the collector also, it may have some resistance. If it does have some resistance, then that will have some thermal noise associated with it. And the emitter can also have resistance, but that resistance is usually very small, so we don't really think about that too much. What else is there? What other events are there? What other kind of noise sources can you imagine there would be? The event of an electron going from the emitter to the collector, right, is indeed a distinct event, right? Either electron eventually will make it to the collector or it's bounced back. So an electron that makes it to a collector has a random time of arrival. And therefore, you would expect it to have some sort of a shot noise effect, because the electrons arrive at random times. They don't arrive on exactly regular intervals, right? So when that happens, then you would expect to have some sort of a shot noise between the collector and emitter. So this would be a shot noise current source, which is 2QIC, right? So that's another source. Now, what else can we have? Well, is there another place where there's some randomness to the events that happen? The time of arrival randomness associated with the currents that you have. How about the base current? Yes, Dave.
Oh, I was going to say recombination.
Recombination, okay, so that's good. Right? Recombination in the base, right? Or the back injection into the emitter from the base. Both of them are events that are distinct and do not happen on exactly regular time periods, right? I mean, so they can happen when they happen. So then you can expect that there would be some shot noise associated with your base current as well, which can be modeled as a current source sitting here. So this would be, so this we should call it IC squared, and let's call this IB squared over delta F. And this one would be 2QIB, the DC value of the base current. So of course it would have less power. It doesn't necessarily mean that it's less important, because why do you think that I'm saying that it may have less? It clearly has smaller power, right? I mean, if it's the transistors in forward active region, IC and IB are like beta, related through a beta, right? IC is beta times larger than IB. But why did I say that IB may not be as or less important than IC?
It's drawing current directly from your input.
It's at the input, especially in a common emitter, for example, arrangement, right? It is putting current into your input, which then gets amplified by beta, or we can think about it as a GM, right? So where the current source appears plays a significant role. That's why, for example, we went through the pain of showing this source here at the base, because that's also at the input. And we'll talk about this more formally shortly. But where the noise source is does affect its impact on the circuit. And we'll see, again, like as I said, we'll see how it affects things shortly. Now, also you can have a flicker noise. So you may have a flicker noise source here too, which would be similar. So you can say IF squared over delta F, which is some sort of a K, some I measure of IC to some power alpha over some F. So it would have a form of that nature. So these are the sources. Now you say, well, that's a whole bunch of sources. What do I do with them? Well, if it's a small signal model, the good news is that it's linear. And if it's linear, you can always use superposition, right? Superposition is our friend in that sense. So we can actually always use superposition to evaluate the effect of these things independently and then look at the aggregate effect of them all combined. Okay, so that's for the BJT and the transistor model for a BJT and a pn-junction diode. How about the MOSFET? Let's go talk about the MOSFET. So in a MOS transistor, what we have really is that we are forming a channel, right? You have a gate, you're forming a channel, which is basically a conductive channel. Let's say it's an NMOS. And then this channel is what's carrying the charge for you. Right? So if I ask you in general, what are the sources of noise that you can have, the channel is really acting like a what? It's a variable resistor, right? It's a resistor. Now, the channel, which has like free charge carriers, if it's acting like a resistor, what do you expect to see? If you're forming a channel, if you're forming a place where there are free charge carriers, you expect them to have random thermal movements, right? So you do expect to see thermal noise in the channel. Now, the thing about the channel is that it's not uniformly distributed. It's not a uniform resistor. So what you need to do, you need to do a similar integration to what we did when we calculated, for example, the total channel charge, or when we calculated, you remember, we got at the 2/3 of the total capacitance, or things of that sort. So if you do a similar thing, then you arrive at a total equivalent channel charge, thermal noise. So I've got I channel over delta F, which is 4 kT. Now, gamma GD0. Now I'll tell you what gamma. Gamma for a non-velocity saturated device is 2/3. And that comes from an integration similar to that capacitance integration. So for non-velocity saturated, sometimes people call it long channel. Non-velocity saturated. Now, in the case of a velocity saturated system, and we'll talk about why this is the case, this quantity can be higher. This can be as high as 2 to 3 or something like that, depending on what happened. And there's some interesting things that happens in that case. We'll talk about that shortly. Now, the other thing that we need to talk about is GD0. What is GD0? Now, this is also one of the things that you may find commonly. This is a common mistake in many textbooks. A lot of textbooks basically just show this as GM. Now, GD0 is the resistance of the channel, or the conductance of the channel, dID dVDS, when VDS is 0. Now, if you think about a long channel non-velocity saturated device, you have an ID that's mu n Cox over 2 W over L VGS minus VT squared. And if you calculate this derivative, obviously what you will get is that you get GD0 is mu n Cox W over L VGS minus VT. This is for non-velocity saturated, which in this case is indeed equal to GM for non-velocity saturated. So if you have a non-velocity saturated device, then yes, this is GM. But that expression is generally true for velocity saturated devices too. If you write it as GM, it's only valid for non-velocity saturated situation. So, and you can see in velocity saturated situation, this part doesn't change. GD0 is still this. So this is always true. Or maybe I should write it slightly differently. No, that's true. And I can say for non-velocity saturated, then GD0 is equal to GM. So this is only true for non-velocity saturated devices, but this is always true for velocity saturated or non-velocity saturated. So in general, we should use this expression. The reason it's not true for velocity saturated situation is that in velocity saturated MOSFET, this is not GM. GM is related to ESAT and things of that sort, or VSAT, things of that sort. But this expression is always true. So in fact, you could write this expression in a longer form. You can write as 4KT gamma mu n Cox W over L VGS minus VT. So you could write it that way anyway. Now, this basically means that if you look at the MOSFET model, so let's look at the small signal model of the MOSFET. So this is GM VGS, and this is VGS. What you can see is that this corresponds to a noise source, right? A thermal noise source between the drain and source, which is basically I channel squared over delta F, which is 4KT gamma GD0. So that's one of the noise sources. That's the main noise source in the channel that you will see. Now, some interesting things happen in a MOSFET, especially in a velocity saturated situation. So in a velocity saturated situation, what do we have here? So you have electrons, you have a whole bunch of electrons in the channel, right? But you remember, this voltage at that point was what? That voltage at that point was a fixed voltage, right? It was a VGS minus VT, right? So the rest of your VDS is really dropped across that area, between that edge and this edge. So if you look at the voltage drop across this thing, you remember we said the barrier looks like this. So it's small here, and then there's a big barrier before you go, a big drop over this distance. So think about it this way. So there are a bunch of electrons moving around here, but there's a large amount of electric field in this area. So the electrons make it to that edge, and then they see this gigantic electric field, and they're like accelerating. And what happens? When they get to this area, because this is highly doped, the cross section becomes much smaller, much larger the impact cross section. So what happens is that they get just absorbed. So they accelerate through here, electron comes here, accelerates, and it slams into this area. Now, it does several different interesting things. One of the interesting things it does that actually, if you monitor it, and people have studied this part of the channel, This part of the transistor is hot because they're just absorbing this energy, right? You're accelerating constantly and then just hitting it. It also can cause damage to the gate oxide around here because these are accelerating, they're hitting here, so they can release other things and they can damage the gate oxide in this area when you have large voltages. So that's one kind of like pretty sensitive area in a MOSFET. But as far as noise is concerned, we can to the first order think about it as that. But there's another thing, but this kind of thing that is happening, that if you have a short channel device, because of the fact that you're actually creating additional fields, you can actually create a channel that has a much higher temperature because of these effects. So the effective temperature of the electronic gas in your channel may not be the actual temperature of the bulk of the silicon sitting here. So it's running hotter here. And that's why this gamma can become larger. And that's why it's kind of like an empirical parameter somewhat. Depending on the exact design of the transistor and all those things, and they may give you a gamma. So, well, this is your gamma for this transistor and things like that. So they're trying to capture all of that in one place. Now, there's one more thing. We talked about modern MOSFETs and the gate oxide being very thin, right? So if the gate oxide is very thin, then you can imagine that there could be potentially current flowing through this. There's tunneling current. Now, tunneling also is a distinct event, right? Either the charge tunnels through the gate or it doesn't. So there's part of that transition. So that can correspond to an actual shot noise here at the gate, which would correspond to, we call it Ig squared over delta F, which would be 2q Ig. Now, if Ig is very small, this current would also be very small. Think about some other things. Think about the MOSFET in 3 dimensions. These are the fingers, right, of the MOSFET. This is basically the gate. There is a resistance. There's a physical resistance, especially when you're making the channel very narrow, right? Because if you're making it L very small to make the transistor fast, the gate fingers are going to be long and skinny, which means that they can have large resistances. So Rg, the series resistance with the gate, can be a significant resistance. And that would, of course, as a physical resistor, will have a voltage noise source, Vg squared over delta F, which would be 4 kT Rg. Right? And then, of course, there's the flicker noise. The flicker noise of a MOSFET is often modeled as a voltage source at the input. So one of the things that you can do, you can say there's a Vf here, or delta F, which is K Cox, K, sometimes we call it Kf, Cox WL times F. So you can see that the flicker noise actually becomes smaller as you make the channel area larger, W and L. The gate capacitance, essentially, the total gate capacitance, will dictate the value of the flicker noise. So the larger your gate capacitance is, the less flicker noise you will get because it's in the denominator. So these are some of the noise sources that you will observe. There are some other things. There's also gate noise, which is basically some of the noise coupled from the channel to the gate, et cetera, that matters in RF amplifiers, especially if you're making cryogenic amplifiers and things of that sort. But we are not too worried about that for the context, for the sake of our conversations. One of the interesting things that you can actually do is that you can say for a MOSFET, if you have flicker noise, and then you have the channel noise, they have different spectra, right? If you think about it, the channel being a thermal noise for the frequencies of interest to us is more or less flat, right? So this is your 4 kT gamma GG0, which for long channel devices or non-velocity saturated devices would be 4 kT gamma GM. On the other hand, your flicker noise, and if this is log of F, your flicker noise, 1 over F noise, will have a spectrum that's like this on a logarithmic plot. Right? So this is basically your KF. So this is basically the input spectrum, right? A voltage input spectrum. Now, if I want to convert it to something that's comparable to this, so I can plot it in terms of the output, what can we do? What should we do? How does this noise, can I take this noise and say, well, there's an equivalent current source here that would reflect that, or model that? If I have a voltage source here, what kind of current source there would produce the same current? What does it need to get multiplied by? By GM, right? Because if I put a voltage here, you have GM times that as a current source here. So one way to think about it is that I can take this out and replace it with a current source here that is GM, but now this has to be GM squared. Where is this coming from? This is coming from that transfer function of a linear system, right? If you have x and y, if you have sx of omega and sy of omega, the sy of omega is related to sx of omega. We talked about this before. Is h of omega magnitude squared. So what is our h of omega in this case? It's gm. Right now we are not taking the frequency behaviors into account. We will do that soon. So it's gm times whatever that is, right? Vf squared over delta f. So whatever you have this expression here times gm squared would be appearing here. So what you have here is really gm squared kf over Cox WL over F. Now there's a parameter that's often talked about for a given transistor, which is called the 1 over F corner frequency. It's the frequency where the power of the 1 over F noise and power of your channel noise are equal. Why does this matter? Because the overall spectrum of your noise, if these were the only two noise sources that you were concerned about, looks like this. This is where the two asymptotes hit. That gives you a measure of what frequency, above what frequency you don't have to worry about flicker noise for that transistor, right? So if I tell you the 1 over F noise corner frequency of this transistor is 100 kilohertz, then you know that if you're making an amplifier that's operating at like 10 gigahertz, you probably don't want to worry about the 1 over F noise, right? Because at that frequency, the channel noise will be dominant, and 1 over F noise, that red curve is going to be way below that. But if you're making an audio amplifier, for example, with the same transistor, the same dimensions, then you need to worry about it because it's 100 kilohertz. So basically it means that you're pretty much dominated by the 1 over F noise. It's a metric that we sometimes use for a given transistor with given size to just get a sense of what frequencies are the ones that we're above which we have to, below which we have to worry about 1 over F noise, right? So you may hear people talk about what is the 1 over F noise corner of this device. Well, for a given device, it basically is where these two things equal. And you can calculate it, right? So you can equate these things and calculate the F. So if you do that, and if you assume it's a non-velocity saturated device, then one of the GMs cancel. So basically what you're doing is that you're setting these two to be equal, right? You're saying this thing, KF, Cox, WLF, F, this is going to be 1 over F corner. It's going to be 4 KT gamma GM for a non-velocity saturated device only. So for that, these cancel. If they are not non-velocity saturated, you just set this as GD0 and solve for it. And then therefore, F1 over F becomes what? It becomes GM KF over 4 KT gamma Cox WL. So that would be where your corner frequency will occur. So these are some of the basic models we will use for analysis of the circuit when we are dealing with noise. Okay? Any questions on that?